All right, the time now is 10:05. As we wait for more of our friends joining our session, I think we can start first with our workshop today. All right, so good morning again, and thank you again for joining us in this workshop. Today we will discover the power of simulation through two of the simulation softwares, and let's take a look. So I'll be taking us through the part one, which is the bubble tea shop simulation with FlexSim, and Hongdan will take us through the second part, which is fish population modeling with Stella Architect. So first thing first, before getting into our simulation, what is simulation and what is FlexSim, the software? Let's have the video here. This video is adapted on the official YouTube channel of FlexSim. So let's watch this 1-minute video together.
What is simulation? You might already know the answer, but if you don't, it can be explained in as little as 2 words. Problem solving. Should we add a new machine? How can we get rid of this bottleneck? Will we receive a positive return on our investment? Simulation can answer these and many other questions because it provides a virtual environment to learn and experiment on your process. A place where data is easy to come by and where mistakes result in improvement instead of ending careers. FlexSim is powerful 3D simulation software, built from the ground up to make simulation as easy as possible, without sacrificing an ounce of function or visual appeal. You can create beautiful, detailed models that deliver results, yet make an impact in the way spreadsheets or charts never could. And you can do it all in just minutes with drag and drop controls and easy-to-use features.
All right, so that's a short intro on simulation FlexSim. And
what is simulation?
oh, sorry. And this is a translation. Sorry, yeah. Okay, yeah. All right. So back to the question, what is simulation and what are models? Because by simulation, we are building models. And models are graphical, mathematical, symbolic, physical, or verbal representation of simplified version of a concept, a phenomenon, and yeah, everything we want to simulate from the real world. We want to build these models so that we can get data, test out different policy scenarios, and get our desired results from our simulation models. But keep in mind that no models are correct, but some models are useful, as we cannot model every detail of the real world, but we can get the part of the world that we are interested in and get our results. All right, so there are many types of simulation as well. And let's say fluid dynamic simulation and other like simulation you can see in aviation and transportation. But today we'll be focusing on two of them. One is the discrete time simulation in FlexSim, and FlexSim is mostly used for warehousing and factories. And the other type is Stella Architect, which is system dynamic simulation. We'll see in part 2. All right, so let's get into our part 1. So we'll be using FlexSim for part 1. So this is the interface layout. If you open up your FlexSim software, all right, let's do this together. So let's go to FlexSim. We should see this window popping up. And in the first screen here, we select classic instead of the healthcare. Then we go to the first button over here called new model. And in this model unit setting, we just keep everything as default and set OK. All right, then this is our main user interface for FlexSim.
Sorry, interruption. Anyone who
Yes.
need us to wait for you, please show a reaction in the Zoom chat, like maybe a raise of hands or anything, so that we know that we are going to slow down. But if you feel the speed is okay, we will proceed.
Yes. So yeah, if you're feeling I'm going too fast, you can slow me down. All right. Okay, so that is the interface, and let's go back to our slides. So in the interface, first we'll have our main menu, similar to all the softwares we use. We have our edits, view, and all these. And below that, we have our toolbar and simulation control bar. Toolbar are some of the features we'll use later, I'll introduce. And for simulation control bar is where we run and play our simulation. So each time we make an edit to our model, we click reset. So save our not as in save, as reset the model to our current state. Then run, by the name suggests, is running the model. Stop here doesn't quite mean stop, it means pause. So once you click stop, you can still click run again to resume the simulation. And lastly, fast forward, skip, all these we will not use today. And one thing I want to highlight here will be the run speed button here. So by default, it's kept at 4, which means 1 second in real life will be 4 seconds in our simulation. And later on, we'll set this run speed to around 60. So 1 second here will be 60 minutes in the 60 seconds, which is 1 minute in the model. Lastly, we'll have our main model interface. Here is the main area where we'll be working on. We'll drag and drop our components into our middle area. And on the left, we have our library. So here are all the assets we'll use later on to drag them and drop into our main menu. All right, so let's take a look at all the library assets we'll be using later on. So first, here's the library that I just mentioned. And first, we have our source. So source is an object that creates flow items, and flow items are the items inside our simulation model. Let's say for factory, the flow items should be the goods that we're producing. And for today, the context is bubble tea shop. So the flow items will be the customers. The customers will arrive, order, collect their orders, and then leave. And this is always the first object we want to place in our model. Yeah, whenever we're using this. Next, we'll have the queue. So queue, by the name suggests, is where the objects will queue up. In the factory, it will be like these. So the goods that are waiting to be processed will queue up inside the queue. And for our scenario, bubble tea shop, will be the customers queuing in one line. Next, we have our processor. So processor is, I'll say, the very important component over here. It will be the server in our queuing system. So in the factory, these goods will be processed one by one on the processor with a given process time. And in our model, the processor will be the customers waiting, or not as in wait, as in taking the order and getting their bubble tea done. And lastly, we have our sink. So sink is where the flow items leave the system. So once a customer finish ordering and collection of the bubble tea, they'll leave the shop through the sink. And by connecting the source, queue, processor, and sink together, we'll get our queuing model. And this is done by the connections. We can connect from one source to queue, connect from queue to processor, and processor to sink. So we should always keep in mind of the direction of these arrows to ensure that our model is flowing well. We'll see this later on in our FlexSim demonstration. All right, so back to our bubble tea shop. This will be the final product of today, our model. So as we can see here, first, the customers will arrive. We don't have a gate here, but yeah, they'll walk into our shop. And next, they will queue for ordering. And they will be ordering at this order taker counter. And after taking their orders, they'll join this they'll join this collection queue where they'll be waiting for their bubble tea to be made. And once they finish collecting their order, they'll leave the bubble tea shop through customer departure. So this is the sync. All right, so let's build this. Oh, right, before building our model in FlexSim, we have this MM1 queue concept here. So what is MM1 queue? Actually, the order queue and collection queue, they are both MM1 queues. So what does MM1 mean? M here suggests Markovian, and Markovian means the arrival rate and service rate both follow the exponential distribution. And for arrival with exponential distribution, we have Poisson process, if you recall from the statistics. Yeah. And all these together will form our MM1 queue. So customer arrive based on a exponential distribution. They queue up in a single queue, and there's only one server. So this is what the MM1 mean. And the server will service based on the exponential distribution service time. And yeah, we will not go too deep into the statistics today. If you are interested in calculating the waiting time, service time, this should be taught in one of our IE, industrial and systems engineering models. All right, so let's jump back to FlexSim, where we can build our bubble tea shop together. Let's go to FlexSim. All right, so I assume that everyone has their software ready if you intend to follow us. And if you have any technical difficulties, you can always Zoom message me, or I think Hongdan, yeah, please message Hongdan, and she'll be helping you to debug any of your software bugs. Yeah. So let's begin. Remember that every time we open up a new model, we should always put in a source first. So we click on source in the library feature sources and click on the empty space in the middle. So here will be our source one. And if you continue clicking, you get a lot of other source. So to exit this adding source mode, we just right click with our mouse. And then our mouse will get back to the normal mouse. Right. Let me delete these unnecessary ones. All right. And so this source is where the customers will arrive. Let's do the relevant settings over here. So we click on source and go to the right properties panel. We should see all the properties related to the source. First thing first, in the flow item class, we need to change from box to either man or woman, since these are the customers in our system. I'll set man for now. And next, we have our inter-arrival time. So recall that for MM1 queues, arrival pattern should follow an exponential distribution. So by default, it's already exponential, but I'll show here how we can set it by ourselves. So we go to the drop-down menu over here, next to the inter-arrival time. Next, we select statistical distribution. Under statistical distribution, we should have exponential. And this panel will show. And what we need to change is the scale parameter over here. So let's say on average, we have one customer arriving per 5 minutes, and our time units is in seconds. So we change the scale to 300 seconds. So each 3 minutes, on average, there'll be one customer arriving. Right. So whether to check the arrival at time 0 is up to you. If you do not want to wait for the first customer to arrive before our model is empty, we can check this checkbox. Lastly, we check the use transport checkbox in the output section, because the customers will need to work on their own instead of the goods in the factory that will need to be carried by our workers or transporters. In this scenario, they'll be working on their own. So we check the use transport checkbox, and in the drop-down menu, we select the second last option here, task executor as flow item. So this means they'll be working on their own. They do not need someone else to carry them around the bubble tea shop. All right, so that's all the settings we need to do for the source. All right, so any question, just stop me anyway. All right, after we have the source, let's have the queue. So this queue is where the customers will queue up. So again, we click on queue, click on the white space. This will bring up queue, and then right click to exit the setting queue mode. In queue, there's not much we need to do, just that from the item placement, instead of step inside queue, we select horizontal line. Because if we do step inside queue, once the queue is full, the customer will start to stand on each other's head, and that's not realistic. So let's try horizontal line instead. And the other setting is the use transport as usual. So we check the use transport, then task executor as flow item. So we need to do these on all the objects for today. That's the queue. Next, we'll have our processor. So click on processor and click on the white space. This is where the customers will take their orders. So now the processor looks like a machine, and customers to stand on the machines, which is not realistic. We'll change this later on. And we need to change the process time. Recall that for MM1 queue, the processing time is also a exponential distribution. So we go to the drop-down menu, statistical distribution, then select exponential again. And here, let's assume that each customer will take around 2 minutes to take their orders. So the average processing time will be 120 seconds. So lastly, let's check the use transport checkbox and set it as task executor as flow item. All right. And one last thing for processor is we need to uncheck the animate items checkbox so that people will not move on the processor like there are goods that are being processed. So now we have our source, queue, processor ready. One last thing, we need our sink. So this is where the customers will leave the shop. I know that we have two queues, one order queue, one collection queue. We'll expand on that a bit later. So for sink, there's no setting we need to do. Yeah, we'll just leave the shop. And once we have the components ready, we'll connect them by connectors. So let's go to A. So connect objects, which is next to the standard mouse mode on the top, the toolbar here. And once we are in connect mode, we should see our mouse become this chain button. So we click on source, then click on queue, and these two components are connected. Next, we click on processor, then click on sync. So all these are connected in one chain. And after sync, we need to leave the connection mode. Again, we right click on our mouse, then right click again. This will bring back our normal mouse. So by doing this, our simple queue is set up. Let's reset and run. We should see that the person arrives, then go to the processor, which is the order taking counter. And now he's taking his order. This will take around 2 minutes. So let's change the run speed of our model to 60 so that it runs faster. 1 second here is 1 minute in the model. right? So we can see that customers are arriving and yeah, taking their orders. Right. So understand that the aesthetics doesn't look quite right here because we need to do a few adjustments later on. For now, let's first disconnect from processor and sync. We'll have our collection queue and collection counter here. So again, for the collection queue, we need to change item placement to horizontal line. Then output, we check use transport, then check the task executor as flow item check. Yeah. And for processor 2 is our collection. So let's uncheck animate items, set the process time as a exponential distribution. And for collection, let's assume that it takes around 5 minutes for each cup of milk tea to be made. So let's have 300 seconds over here. And lastly, for U transport, yeah, again, check the task executor as flow item. So once we do all these settings for the processor 2, we can connect them again using the connect mode here just now. So we connect from processor 1 to Q2, which is our collection queue, Q2 to processor 2, which is our collection counter, and lastly connect to sync, where the customers will leave the system. All right, so this is our bubble tea shop general structure. Let's reset and run. You can see that the customers who are first taking the order and next getting their collection. And then you need to queue up for their milk tea to be made. If you want to play faster, we can set the run speed faster as well. All right. So by doing this, we already have our model working. Let me see how much time I have left. I have 3 more minutes. All right. So we can go into a bit of the analytics. If you are interested in making our model into the one that's shown over here. So this is after getting all the other 3D models done and getting the dashboard. If you're interested in this, you can let me know. I can walk you through this after the our workshop duration. Yeah, because we're running short on time. Yeah. So this is what it will look like after we make all the analytics done. So just to demo to everyone, I just add a wooden floor over here. Beneath the floor is actually our queue and processors. So, and these are walls and tables are just the 3D models without functions in our simulation. So you can see here the customer will arrive, then still queue inside the queue, then go to the processor for their order taking and collection. And they'll leave. Yeah. Just to make everything looks nicer, I add this layer of the floor. Yeah, so that it looks more like a proper bubble tea shop. And if you take these industrial and systems engineering course, we actually see how we can observe our data through our simulation. So for each simulation model we build, there's a purpose. And for this case, we'll be observing within 1 day, how many customers are we serving? What is the average queue length? How many people are in the queue? And what is the average queuing time? So how long you need to wait before you can get your bubble tea? Right. So due to the time constraint, I cannot go through everything here today. But if you're interested, just can leave me a message or drop me an email. I'm glad to intro all these contents to you. All right, so that's all for my demo. Let's go back to our slides. All right. So the bubble tea shop here is just a very simple use case for the FlexSim simulation. Apart from these, we also have some industry applications we do with our students. So this is one SDP, standing for System Design Projects, that we have for each of our IEC students in year 3 or year 4. And 4 or 5 students will form up a team and work with one company that has collaboration with our faculty. And SETS is a in-flight catering company that will provide the in-flight food and drinks for the Scoot and Jetstar airlines in this scenario. And this is the model they built for SETS. So this is their factory. So you can see that inside this model is much more complicated than our bubble tea shop just now. So the workers are working around the factory to take and pack their in-flight carts. So all these carts are the pushing carts you can see in your flights. And by building these dashboards, we can get a lot of useful information for each simulation scenario. Right, so that's all for my part of sharing. Now I'll hand the time over to Hongdan, who will take us through the second part of our workshop. Right, thank you for listening for my part.
Okay, great. Thanks, Li Cheng. Wow, his model looks very atas. Then my one is quite simple. But just hope y'all to get a touch, get your hands onto it. Just try to see how useful it is in solving real world problem, and hope the experience is fun. So let me share my screen right now. Okay, so just now, as mentioned by Li Cheng, right, there are many ways of doing a simulation model. Just now, the FlexSim, the software, is more often used for discrete event simulation. So those kind of event simulation is to solve problems in like warehouse, logistics, supply chain, and even port logistics, right? And then there are other problems in the real world that you want to solve. Those could be social, economical problem, ecosystem problem that the system might be more complex, bigger, and like you want to improve the system performance. For example, you want to improve the sustainability of biodiversity in the environment, or you want to improve like a human health system to stop a pandemic transmission. So this kind of thing, you need different software, different formalism to help you build this simulation model, such that the real world scenario is simplified enough into your machine, and then you can just play this model and try different hypotheses, policy design scenarios on it, such that you are able to aid decision making. And today we're going to try this system dynamics modeling in the case study of the shrinking fish industry. So this is our story context for today. So we're going to simulate a fragile ecosystem. So you imagine this coastal region, people living there, they will do fishing for a living. So originally the fishes in the sea fisheries are very abundant. They are making a sustainable living, but one day they decide to build more boats so that they can catch more fishes and then generate more revenue. But over time, they realize the fish stocks in the fishery is starting to decline. The fish population collapse, and then the community would worry, are we taking too much? Can really the ecosystem sustain our catch amount? How are we going to preserve our environment and source of living? So today we use system modeling to help us solve this challenge. Okay, so instead of doing the model from scratch, I will send you guys a half-done model so that we just need to have a touch up on it. Okay, let me go to my Zoom settings right now. Okay, if you look into your chat box in Zoom, you should be receiving a file called fish population model. And then you can download from there. So what we do right now is let's try to get our hands on it. We need to open our software first. So this software is called Stella Architect. STELLA. Then you go to the software, open it. And then you will be able to see this working platform for you to build simulation. It's quite similar, structure is quite similar. On top is the control panel where you have all the elements you need to build the simulation model. And then we need to go to File on the top left corner and click Open a File. Then you should find the fish population model that you download just now. Maybe it's in your downloads or other places. Right. Click fish population model, open it. So the black part is the part for the fish population. And then on the bottom left corner, you have this play button. This play button is to run the simulation model. And then you click run. This simulation model will be able to show how your fish population will change over time from year 2022 until year 2052. And then we can see the fish population is very stable and in equilibrium during this 30-year period. Okay. Sorry about just now the bug. I still want to laugh, but can show a hands from the audience, like show any reaction from the audience that you need me to wait for you to open the software if you want to follow me through this simulation process. If you need me to wait for you, you just show me a hands in your reaction. If not, let's continue. Go back to our slides. Okay, just now I've walked you through this fish population, like this Stella Architect working platform. We can see these menus and buttons and then the fish population model. And then when you double click on this white space, this white canvas, you will be able to get the model settings panel. This is the property panel that we're going to set off for all the elements inside the model. Okay. About this structure, let me just have a quick walkthrough with you guys. What does it mean and what is telling? So you imagine a fishery with 1,000 fish at first. So you have 1,000 fish in your fishery, and then all your fishes are stored in this rectangle box. And each year, new fish are born and some fish die naturally. So whenever you have new fish being born, they will enter this box, and then whenever they die, they will leave this box. So the analogy is like water sink pipe analogy. You have this sink as a stock. It indicates the amount of fish that you have in this sink. And then whenever you have newborn, right, you have inflow of water. So the water is like your fish. You have inflow of water. And then whenever the fishes die, they will flow out of the sink. So they are represented as outflow. So birth and death over time are represented as these arrows here. They are pipes. And then we know that the number of fish born each year depends on the size of the current population and the average fractional birth rate. So what this means is that the number of fish born each year depends on the current amount of fish. The more fish population you have, the more newborn babies you will have. And then the equation for birth per year is indicated as mathematically using the current fish population times the birth fraction. And similarly, the number of fish that naturally die each year depends on the death fraction and the current population. So similarly, the more fish you have in your fishery right now, so every year the amount of fish that die would be larger because your population base is larger. So the death per year is equal to fish population times death fraction. And then continue, there is an interesting concept incorporated inside this model is that the fraction of fish that die each year depends on how close the population is to the fisheries carrying capacity. So what fisheries carrying capacity mean here is the optimal amount of fish that this fishery can hold. And then whenever your population grows closer to it or surpass it, right? Like the fishes will compete for food, oxygen, resources, and then when the competition is too much, they will die faster. Right, so this kind of relationship is also built inside our model. And then eventually we get this. So you have this fish population as the stock is the water sink, right? And then you have newborn as fish hatch rate and fish death rate as the water pipes to add on more fish and remove more fishes. And then the birth fraction, hatch fraction, and carrying capacity, death fraction, they are calculated and inputted just as what we described just now. And then just now, I also showed that when you run the play button, you are able to see that the fish population is under equilibrium in the long term. And then what we are trying to do is to model the fishing activities here. We try to see what human can do to the fishery. And then we are going to add on the blue parts. So we know that whenever the fishes are caught by human, they are taken out of the fishery. So how much we catch per year is indicated by this outflow. And then there are also other factors affecting it, such as the density of the fish population over the fishery area and the number of ships that you have, like the number of equipments that you have. Like the more equipment you have, the more fish you will catch, right? So these are influencing factors, and we are going to do this together. So first, like apart from being born and dying naturally, fish might be caught by fishing vessels. So we need to draw an outflow for this fish population. So we go back to our software. Okay, you can see on top, these are the components that you need. And when we want to draw a flow, you can see this second icon here is a flow. You click once on it and just release your mouth, and you can see this flow pipes hovering over your canvas. You move it on top of fish population. Click and hold, don't release, click and hold and drag it downwards. Then you are creating a flow, an outflow from the fish population stock. And then we name it as total catch rate. Okay, anyone in the audience need me to slow down here? Are you able to do this? Okay, great. Now continue. Going back to our slides. Okay, the next concept is that the fish caught per ship depends on the density of the fish in the fishery. So what does this mean is that like you are assuming that your fishery area is fixed. And the more fish you have, the more dense the fish population is to spread across this fishery area. And whenever you go and spread your net, right, you are able to catch more fish. So we are going to illustrate this inside our model. So what we need is two components, which is the area of the fishery. The other one is the catch per ship. So let's create these two components together in our model. So instead of using the pipe just now, we use the third icon, which is the converter here. So basically, it's just a placeholder for you to hold information. Converter, first one is area. We are assuming that the area of the fishery is 100 units. So we just put on 100 here. How do we open this side panel is that you just need to double click on this area component, then you are able to edit the property of it over the right hand side. So you have this equation area and then enter the area as 100. The next converter that we need is catch per ship. So similarly, we select this circle converter and drop it onto the canvas. Catch per ship. Just now we have said that the amount of fish that you can catch by a ship during one activity depends on the fish population density. And then how density is calculated is using fish population divided by the area, right? So we need to connect these two together. So how to do it is that you use the fourth icon, so which is a pink arrow, select, then you can see the icon hovering here. Put it over fish population, clip, don't release and drag. Drag it into catch per ship. And we know that, and double click on catch per ship, we're able to enter equation here. We know that the catch per ship is related to fish population density, which is calculated by fish population divide the area. So how do you enter this equation here is that you can see the required inputs on top, meaning that these required inputs, they are connected by your connector to this catch per ship. And then you will need these inputs in all these inputs inside your equation. So we just click on fish population. You will be able to see it appear here. Click. And we need a divide operator, area. Just click on area. You'll be able to get this equation. Right. Can anyone need more time to follow this? Show me your hands up inside the erection. Anyone have done like successfully following me until now? Can you show me a thumb up? I want to see who is following. Hey, yeah, I got people following. Great. Thank you so much. Got encouraged. Okay, so after this, right, we're going to do a more difficult equation setting. So what you need to do is to find this graphical tab. You can see right now the tab is x squared, meaning you are inputting equation. The next one is graphical function. So this is a tab that you need to click on. So we're going to input a graphical input. And now it's graphical, right? Now it's grayed out, and you need to tick this graphical on top. meaning that you're activating it. And we need to adjust the settings. Let's see what's the settings. Okay, just follow me. After you come here, right, you can see a graph. The first thing you need to do is to set the axis scale. So we can see the bottom part. Bottom part is fish population over area. So this is your fish density. So I want to adjust the scale to 0 to 10. So I just need to adjust the upper level to 10. Then for y-axis, I'm changing it to 25. So what this graphical function means is that it illustrates the relationship between fish density as an x-axis and then your catch per ship as an independent variable. It just illustrates the relationship between these two. And we need a curve. So we go to preset shape at the bottom. We will need to select the third one, which is this logarithm growth. Just click on it once. And then this preset shape will appear on your graph. And then we want to adjust the curvature by moving the glider at the bottom. And today we are going to choose a value around 3. Don't ask me why. This is just assumption. We just need a curvature like this. So gradually move until 3 or around 3. Small deviation would be okay, but try to hit 3. After we get the 3 right, we can see this graph. What does it mean is that the more like fish density you have inside your fishery, the more catch per ship you can get. But the catch per ship will eventually reach a limit because this is your equipment limit. You can maximally catch 25 fishes per ship. Okay, so this is graphical input. Anyone need help for this? Need me to slow down or need me to show again? Okay, great. Let's go back to our slide, see so what's next. So after this, okay, so this part says the total fish catch per year is the product of the catch per ship and the size of the fishing fleet. So you need to have this converter, number of ships, and then you need to connect catch per ship and number of ships to total catch rate. So let's do this together. Create a converter. So you need to go to this small circle to hold information. Click, drop, get this ships. All right, and then we need connector to connect these two together to total catch rate. So click on it, press, hold, don't release, connect. Then the other one is the same, press, hold to total catch rate. And then we know that total amount that you can catch is equal to catch per ship times the number of ships. Yeah, just need to click on the required input. You will be able to get it. And then we have finished setting the total catch rate function. And then after that, the slides asks us to set the number of ships to 19, but I think we can set to 20. So this means originally you have, okay, you are deploying 20 ships in your fleet to go and catch fish. Now we're done with our model. And then we can see that originally the fish population is very stable and we want to see what will happen next by clicking on play. Oops, the fish population collapsed over time. So you're seeing that you are overfishing. Okay, any questions from the audience? Okay, for those of you who have followed me through, here is an interesting exercise question that I want you guys to try. So It says refer to the fishing activities model, conduct experiment for different values of number of ships. What is the maximum number of ships to maintain a sustainable fish population over the 30 years? So it gives numbers 17, 18, 19, and 20. What does it mean is they want you to adjust this number. So you double click on ships, adjust this number to different numbers like 20, 19, 18, 17. Right, and see which number will get you a fish population that won't be depleted until 0. Do you want to take some time to try? And do it together lah. Okay, because I cannot see your screen from Zoom. So right now, 20 ships is depleted. And then let's try 19. Play. Oh no. Even though it's lower, it's still reaching 0 at the end of 30 years. And then we try the number of ships as 18. Seems okay. It's still declining, but it won't reach 0. So maybe after 30 years, I have a new set of new team of government policymakers coming in, can change the fishing policy and then improve the fish stocks later. But so far during this 30-year period, still look okay. And then if we need 17 ships, performance is much better. Seems like it's reaching an equilibrium. So it seems like 17 ships is quite sustainable over the long-term period, even after 30 years, but 18 ships is still doing okay. So that is an example, example of how we do scenario testing and on policies, right? Like to test what is the optimum choice, to give insights to the decision makers. Okay, hope you have enjoyed our demonstration so far about how to do a simulation dynamic system modeling. And I'm just going through a little bit on how how the system dynamics modeling is used in real world applications. It's often used on social economic problems, like simulate the pandemic transmission, for example, the COVID-19 scenarios, how human immunity changes with antibiotic usage and how this would affect disease transmission. And also it is used on ecosystem problems on sustainability, like water system, biodiversity system, food, agriculture, and energy, to connect all these different parts together such that people can see the complex and big system as a whole to make the optimal decision, because we know that when one part is changed, the other part is changing also. And sometimes the system is so big, you are not able to observe them by the same group of people or at the same time. So you need this model to help you to see what are the relationships and then to help you make better decision making. Okay, that's all for the demonstration, and I hope you have enjoyed this session. And before we end the session, I'm going to advertise on our upcoming City Open Day event for ICM. We invite our freshmen to be to campus to know better about different engineering courses, or for us, welcome to see our booth at Industrial System Engineering. So how you get there is on this menu. I'll send this menu later to our group chat on Zoom. You can download it. This is transport information. And then what is important is on the 4th page, you have this registration QR code you need to scan to go for the open house. You can save a screenshot here, or later you just use this QR code that I'll be sending to you. And this is the location about different booths. and you will be able to have different tours that like a current undergraduate student will guide a group of students to see different project rooms, labs, media rooms. You'll be able to explore the university facilities, directories. Okay, great. So let me share it right now to everyone. Take some time. Okay. Once again, we thank you for coming to this simulation workshop and hope you have a very enriching experience in simulation. Do
Thank you.
anyone have any questions? Yes, I can see the hand clapping. Thank you so much. Got encouraged. Anyone wants to ask about any questions about ICM or anything, or like our experience in university? Both of us, me and Li Cheng, used to be undergrad ICM students. Now we're continue to be teaching faculty. Yeah. Any questions on like campus life or anything?
And apart from that, I also like to actually just share the property model from FlexSim just now, because we didn't have enough time to go through all the aesthetic settings. Yeah, so I'll just share this file in our Zoom chat as well. So if you have downloaded the FlexSim software, you can play with the model as well. All right, it's in our chat box.
Great. If no questions, everyone, thanks for your time on a Saturday morning, and you are able, like, you may leave this Zoom meeting. Thank you so much.
Thank you.
Cut.